Right now, somewhere above you, beyond the blue of the American sky, beyond the thin line where airplanes carve white scars across the atmosphere, beyond the orbit of satellites carrying your GPS, your calls, your late-night scrolling, there are more than 200 billion stars in our galaxy alone. 200 billion suns. And that's just the Milky Way. Many of those stars are billions of years older than our own sun. Think about that for a second. Billions of years older. In the United States, we measure history in centuries. The Constitution is less than 250 years old. The dinosaurs vanished 66 million years ago. But in cosmic terms, that's nothing. If another civilization had just a 1 million year head start on us, a blink in galactic time, they could have spread across the entire Milky Way by now. They could have built structures around stars. They could have engineered entire solar systems. They could have turned their home planets into shining beacons. They could be everywhere. And yet, when we point our most powerful radio telescopes into the dark, when we scan the sky with instruments built by NASA, when we listen across frequencies for whispers from distant worlds, we hear nothing. No signals, no alien broadcasts, no evidence of galactic empires, just silence. A vast, cold, unbroken silence. So here is the question that keeps scientists awake at night. The question that once stopped a room full of physicists in their tracks. If the universe should be full of life, where is everybody? Before we dive deeper, if you love exploring the biggest mysteries of space and the universe, hit like, subscribe, and turn on notifications so you don't miss what's coming next. And I want to know, from which part of the United States are you watching right now? Are you in California under those wide Pacific skies? Texas under open plains? New York with city lights drowning out the stars? Florida near Cape Canaveral where rockets rise into orbit? Drop a comment and tell me your state. I read them, now take a breath. Because tonight, we begin crossing one of the strangest, most unsettling ideas in science, the Fermi Paradox. The paradox is named after the Italian-American physicist Enrico Fermi, one of the architects of the nuclear age, a man who helped build the first nuclear reactor and contributed to the Manhattan Project. In 1950, during a casual lunch conversation at Los Alamos, Fermi reportedly asked a simple question: where is everybody? He wasn't joking. He wasn't being poetic. He was doing math in his head. Fermi understood the scale of the galaxy. He understood how long it had existed, over 13 billion years for the universe, around 13.6 billion, and about 4.6 billion for our solar system. He understood how quickly technology can evolve once intelligence appears. In just over a century, humanity went from horse-drawn carriages to walking on the moon, from the Wright brothers to the International Space Station, from primitive radios to interplanetary probes like Voyager. If technological growth continues even modestly, it doesn't take millions of years to spread across a galaxy. It might take tens of millions. A long time for us, but a blink in cosmic history. Even traveling at a fraction of light speed, a civilization could hop from star to star, colonizing systems, building self-replicating probes, spreading like a slow but unstoppable wave. And since many stars in the Milky Way are billions of years older than the Sun, if intelligent life arose even once before us, it should have had more than enough time to expand across the entire galaxy. The Milky Way should be buzzing. We should see megastructures blocking starlight, artificial radio emissions, industrial pollution in exoplanet atmospheres, something. But we don't. To understand why this is so disturbing, we need to look at the numbers. Astronomers estimate that the Milky Way contains between 100 and 400 billion stars. Many of those stars have planets. In fact, thanks to missions like NASA's Kepler Space Telescope, we now know that planets are not rare accidents. They are the rule. Most stars have planetary systems. There may be hundreds of billions of planets in our galaxy alone, and a significant fraction of those planets exist in what scientists call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water, the molecule that makes life possible on Earth. 2 hydrogen atoms, 1 oxygen atom. Simple common. Hydrogen is the most abundant element in the universe. Oxygen is forged in the hearts of stars. The ingredients for life are everywhere. When we look at our own solar system, we see hints that life might not even be rare here. Mars once had rivers and lakes. Jupiter's moon Europa hides a vast ocean beneath its icy crust. Saturn's moon Enceladus shoots plumes of water vapor into space. Titan has lakes, not of water, but of methane and ethane. If life can emerge wherever there is chemistry and energy, then the galaxy could be teeming with biology. So why don't we see civilizations? In 1961, astronomer Frank Drake attempted to formalize this question with what is now known as the Drake equation. It isn't really an equation in the traditional sense, it's more of a framework. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction of those that develop life, the fraction that develop intelligent life, the fraction that develop detectable technology, and the length of time such civilizations release signals into space. Each factor is uncertain, but even conservative estimates often suggest that there should be multiple technologically advanced civilizations in our galaxy right now. And yet, every time we listen, nothing. This is the Fermi Paradox, the contradiction between high probability and zero evidence. Let's break it down further. Imagine the Milky Way as a vast ocean. Stars are islands scattered across a dark sea. Our Sun is just one island among hundreds of billions. The nearest star system, Alpha Centauri, is over 4 light-years away. That's about 25 trillion miles. Our fastest spacecraft would take tens of thousands of years to get there. Space is unimaginably vast, but the galaxy is also ancient. If a civilization arose a billion years before us, which is entirely possible given the age of many stars, even slow expansion would eventually reach every corner. Consider self-replicating probes, sometimes called von Neumann probes after mathematician John von Neumann. The idea is simple: build a machine that can travel to another star system, use local materials to create copies of itself, and send those copies onward. Each probe builds more probes. It's exponential growth. 1 becomes 2, 2 become 4, 4 become 8. Within a few million years, the entire galaxy could be explored or colonized. We have the theoretical capability to imagine such machines. A civilization just a few thousand years more advanced than ours might build them. And if even one civilization ever did, the galaxy would not be silent. We would see artifacts, we would detect anomalies, we would find something that doesn't look natural. But we don't. Radio telescopes scan the skies. Projects like SETI, the Search for Extraterrestrial Intelligence, analyze vast amounts of data searching for narrowband radio signals that nature does not produce. We've searched for decades, we've scanned millions of star systems, and while there have been mysterious signals, like the famous WOW signal in 1977, none have been confirmed as alien. Silence. So what are the possible explanations? Before we explore the terrifying ones, we need to understand the foundation. Maybe the universe isn't as life-friendly as we think. Life on Earth began relatively quickly after the planet formed. The Earth is about 4.5 billion years old. The earliest evidence of life dates back at least 3.5 billion years, possibly earlier. That suggests that when conditions are right, life might emerge readily. But there is a massive gap between simple life and intelligent technological civilization. For most of Earth's history, life was microbial. Single-celled organisms dominated for billions of years. Complex multicellular life only exploded around 540 million years ago during the Cambrian explosion. Intelligent tool-using humans, we've existed for maybe 200,000 years. Technological civilization. A few hundred years. That timeline raises an uncomfortable possibility. Maybe simple life is common, but intelligent life is extremely rare. Evolution does not have a goal. It does not strive toward intelligence. Dinosaurs ruled Earth for over 160 million years and never built radios. Sharks have existed for over 400 million years without writing poetry or launching rockets. Intelligence might be an evolutionary fluke, not an inevitability. And even if intelligence arises, technology might not. Consider the environmental stability required for civilization. Earth has had a relatively stable climate for thousands of years, allowing agriculture to flourish. If a planet is too volatile, constant asteroid impacts, unstable star, intense radiation, complex life may never survive long enough to evolve technology. Our own planet has suffered mass extinctions. An asteroid impact 66 million years ago wiped out the dinosaurs. Massive volcanic eruptions have altered climate. Ice ages have frozen continents. We survived. But what if most planets are less forgiving? Another factor is time. Our civilization has been broadcasting radio signals into space for just over a century. That's a tiny window. After only 100 years, we're already shifting toward more efficient, less broadcast, heavy communication technologies like fiber optics and tight beam transmissions. It's possible that the radio loud phase of a civilization is brief. If so, the overlap between civilizations might be rare. We might be listening at the wrong time. But even that explanation feels incomplete. The galaxy is so old that even rare overlaps should happen occasionally. Here's where the paradox deepens into something darker. What if civilizations don't last? The moment a species develops advanced technology, it gains the power to destroy itself. Nuclear weapons, engineered pandemics, artificial intelligence gone wrong, climate change, ecological collapse. The same intelligence that allows a civilization to reach the stars also allows it to annihilate itself. Perhaps there is a great filter, a stage in evolution that is nearly impossible to pass. Maybe almost all civilizations destroy themselves shortly after developing technology. Maybe the silence is not emptiness, but graveyards. If that's true, the question becomes terrifyingly personal. Is the great filter behind us, meaning we are rare and lucky, or is it ahead of us? But before we go there, we must continue building the case. We must understand the scale of the cosmic arena in which this question unfolds. The observable universe contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. The number of planets likely exceeds the number of grains of sand on all the beaches of Earth. Modern astronomy, powered by telescopes like Hubble and the James Webb Space Telescope, has revealed exoplanets of astonishing diversity: super-Earths, hot Jupiters, water worlds, rogue planets drifting between stars. Some orbit red dwarfs, the most common type of star in the galaxy. Red dwarfs live trillions of years, far longer than the Sun. If life can survive around them, there has been more than enough time for ancient civilizations to arise. And yet, no Dyson spheres, no galaxy-spanning empires, no unmistakable signs of engineering on a cosmic scale. The night sky over America looks peaceful, but scientifically it is screaming with contradiction. The math says we should not be alone. The evidence says we might be. Some scientists argue that we are early, that intelligent life takes far longer to develop than we assume. Maybe we are among the first. The universe is 13.8 billion years old, but heavy elements like carbon and oxygen had to be forged in earlier generations of stars. Perhaps only in the last few billion years did the universe become chemically rich enough for complex life. If so, maybe we are pioneers standing at the dawn of cosmic intelligence. But that idea carries its own weight. If we are early, then the future of intelligence in the universe depends on us. The responsibility is enormous. As we close this first chapter, we stand at the edge of a mystery that challenges everything we think we know about life, evolution, and our place in the cosmos. The Fermi Paradox is not just a scientific puzzle. It is an existential mirror. It forces us to confront uncomfortable possibilities: that life is rare, that intelligence is fragile, that civilizations self-destruct, or that something out there is deliberately silent. We began with a simple question: where is everybody? If the galaxy should be alive, and it isn't, then something is stopping life from spreading. In Chapter 1, we built the paradox: hundreds of billions of stars, trillions of planets, billions of years of cosmic time. Even conservative estimates suggest that intelligent civilizations should have emerged many times before us. And yet, the sky remains silent. Now we step into one of the most powerful and most terrifying ideas ever proposed to explain that silence: the great filter. The great filter is not a single event. It is a barrier, a stage in the evolutionary path from lifeless matter to galaxy-spanning civilization that is incredibly difficult, perhaps almost impossible, to pass. The concept was popularized by economist Robin Hanson in the 1990s, but the logic grows directly out of the Fermi Paradox itself. If the path from dead rock to advanced civilization were easy, then the universe should already be filled with visible, ancient, technologically powerful societies. Since it is not, something along that path must be extremely rare. To understand the great filter, we need to break evolution into steps. First, a planet forms in the habitable zone of a star. Second, basic chemistry organizes into self-replicating molecules. Third, simple life emerges. Fourth, complex multicellular life evolves. Fifth, intelligent life capable of abstract thought appears. Sixth, that intelligence develops advanced technology. Seventh, that civilization survives long enough to expand into space. If even one of these steps is extraordinarily improbable, then intelligent civilizations could be rare. And if one of the later steps tends to destroy civilizations before they spread, that could explain the silence. So here is the chilling question: where is the filter? Is it behind us, or is it ahead of us? Let's start at the beginning. Life on Earth began relatively quickly after the planet cooled. Geological evidence suggests that within a few 100 million years, simple microbial life existed. That might suggest that abiogenesis, the transition from chemistry to biology, is easy. But we only have one data point, Earth. One success does not tell us how many failures there were across the galaxy. It's possible that the origin of life is an almost miraculous event, so unlikely that it has only happened once in the Milky Way. If that's true, then we are not just rare. We are unimaginably rare. The silence of the cosmos would not be tragic. It would be expected. But here's the problem with that comforting idea: the universe is chemically rich. Organic molecules form naturally in interstellar clouds. We've detected amino acids in meteorites. The building blocks of life appear to be everywhere. Water is abundant. Carbon chemistry is flexible and complex. The early Earth was a chaotic laboratory filled with energy from lightning, volcanic heat, ultraviolet radiation. If chemistry can stumble into life here, why not elsewhere? Now move to the next step: complex life. For nearly 2 billion years, life on Earth remained single-celled. Bacteria dominated. Then something extraordinary happened. Cells began cooperating. They merged. They specialized. This process, known as endosymbiosis, likely led to the development of complex eukaryotic cells. Without it, animals, plants, and fungi would not exist. Some scientists argue that this step may be incredibly rare. It required one cell to engulf another without digesting it, and for both to benefit from the relationship. A delicate evolutionary dance. If complex cells are rare, then intelligent life may be vanishingly uncommon. Then comes multicellularity, then nervous systems, then brains, then self-awareness. For most of Earth's history, no species built cities or telescope. Dinosaurs thrived for 160 million years and never launched satellites. Intelligence, at least the kind capable of advanced engineering, may not be evolution's default destination. It may be a strange side branch. But even if intelligence evolves, another filter may wait: technology. Humanity developed agriculture around 10,000 years ago, writing around 5,000 years ago, industrial technology only a few hundred years ago, radio barely more than a century ago, nuclear weapons less than 80 years ago, artificial intelligence, in its modern form, only decades old. Technological growth is explosive, but it is also dangerous, and this brings us to the darker interpretation of the Great Filter. Perhaps life is common. Perhaps intelligence evolves often. Perhaps civilizations rise across the galaxy again and again, and perhaps they all destroy themselves. Think about our own trajectory. We split the atom in the 1940s. Within years, we had weapons capable of ending civilization. During the Cold War, the United States and the Soviet Union amassed enough nuclear warheads to wipe out human life many times over. A few miscalculations, a few miscommunications, and our story could have ended before we ever launched deep space probes like Voyager 1 and Voyager 2. And nuclear war is just one threat. Climate change, driven by industrial emissions, is altering Earth's atmosphere. Biodiversity is collapsing. Oceans are acidifying. Pandemics can spread globally within weeks due to air travel. Artificial intelligence is accelerating faster than many experts predicted. Synthetic biology allows us to edit genomes. The power to reshape the planet or accidentally devastate it now rests in human hands. If this technological adolescence is a universal stage for intelligent species, then many civilizations might never reach maturity. They might ignite briefly, a flash of radio signals, industrial pollution, satellite networks, and then collapse into silence. Their cities crumble, their signals fade. Within a few million years, geological processes erase most traces of their existence. On cosmic timescales, that is nothing. This idea reframes the silence of the universe not as emptiness, but as aftermath. The sky may be quiet because it is filled with ruins too distant for us to see. But here is the truly terrifying part. If the Great Filter lies in our future, then the silence is a warning. Consider the timeline of a typical star. Our sun will shine for about 10 billion years. It is currently about 4.6 billion years old. That leaves roughly 5 billion years before it expands into a red giant and engulfs the inner planets. Humanity, by contrast, has had advanced technology for barely a century. If we survive for even 1 million years, just 1 million, we would already be ancient compared to our current age. If we survive for 1 billion years, we could reshape entire solar systems. So why don't we see evidence of billion-year-old civilizations? Because maybe almost none survive that long. The Great Filter hypothesis also connects to another concept, the rare earth hypothesis. This idea suggests that while microbial life might be common, the combination of factors that made complex life possible on Earth is extraordinarily rare. We have a large moon that stabilizes our planet's axial tilt. We have plate tectonics recycling carbon and regulating climate. We have a magnetic field shielding us from solar radiation. We orbit a relatively stable star. We exist in a relatively calm region of the galaxy, away from frequent supernova explosions. Each of these factors might be uncommon. Together, they may form a narrow window of habitability. If so, Earth could be a cosmic oasis in a vast desert. But even that may not solve the paradox, because even a few advanced civilizations over billions of years should leave detectable footprints, unless they don't want to be detected, or unless something removes them. Astrophysical threats could also act as filters. Gamma-ray bursts, the most energetic explosions in the universe, can sterilize planets across vast distances. Supernova can bathe nearby systems in lethal radiation. Massive asteroid impacts can reset biological evolution. Perhaps the galaxy is more hostile than we realize, repeatedly wiping the slate clean before intelligence can spread. Yet our region of the Milky Way appears relatively stable. Earth has avoided total sterilization for billions of years. So why not others? The power of the great filter idea lies in its simplicity. It doesn't require exotic physics. It doesn't require hidden alien empires. It simply says that somewhere between dead matter and galaxies spanning civilization there is a step so improbable or so dangerous that almost no species passes it. Imagine a vast cosmic race. At the starting line, lifeless planets. At the finish line, civilizations capable of colonizing the galaxy. Between them, a series of gates. Most competitors never make it through the first. A few reach the middle. Almost none reach the end. Where are we on that track? If microbial life is common, and future missions to Mars, Europa, or Enceladus discover independent life forms, that would suggest that the early steps are easy. In that case, the filter likely lies ahead of us. That would be terrifying, because it would mean that almost every civilization that reaches our level eventually hits a wall. But if we explore our solar system and find nothing, no second genesis, no alien microbes, that might suggest that the filter is behind us. The origin of life itself could be the miracle. In that case, we may already be the survivors of the hardest step. Either possibility is profound. The great filter forces us to confront our fragility. We like to imagine progress as inevitable. But evolution does not guarantee survival. Intelligence does not guarantee wisdom. Power does not guarantee restraint. The silence of the stars might not be a mystery to solve. It might be a mirror. As we advance into artificial intelligence, biotechnology, space colonization, and planetary engineering, we are approaching thresholds no species on Earth has ever crossed. We are conducting an experiment with no control group, and the universe offers no examples of long-lived technological civilizations to guide us. Or perhaps it does, and we simply cannot see them. That advanced civilizations are not absent but invisible, that they may deliberately hide, observing quietly in what some scientists call the dark forest. A universe where silence is not accidental, it is survival. If the great filter is about extinction, the dark forest is about fear, and it may change the way you look at the night sky forever. For now, sit with this thought. The universe is either empty because life is impossibly rare, or it is empty because intelligence tends to erase itself. Both answers are heavy, and we are only beginning to understand what they mean. Before we go deeper into the next terrifying possibility, make sure you subscribe and turn on notifications so you don't miss the rest of this series. We're crossing 30 of the most mind-bending, unsettling explanations ever proposed for the Fermi Paradox, and each one changes how you see the universe. If you're fascinated by space, the cosmos, black holes, exoplanets, NASA discoveries, and the biggest mysteries of our solar system and beyond, this is where you want to be. And don't forget, drop a comment telling me which state you're watching from. Are you under the desert skies of Arizona, the mountains of Colorado, the city lights of New York, the beaches of Florida? I want to see how far this signal is reaching across America. Now let's continue.